Okay, so in that GCF, bx to the m is 0. Okay, what about b though? Well, notice that we have 1 here. Wait, let me get the laser. We have 1 here, right, as a coefficient. But what are the factors of 1? Well, the only factors of 1 here is 1. What about 3? Well, the only factors of 3 are 1 and 3. So what's the greatest common factor? Well, it's 1. So b has to be 1. The GCF here is then 1 times x to the 0, which is 1. That's what this is equal to. 1 times x to the 0, which is 1. And again, this was left over after we factored out the GCF from the original polynomial. So this thing left over has a GCF of 1. Okay, well, that's no accident here. In fact, so we did this. In fact, if you're factoring out if you find and factor out the GCF of a polynomial, okay, the polynomial that's left over, that's going to have a GCF of 1. So again, it's just like over here, right? This was the original polynomial. We found the GCF and we factored it out, okay? What's left over? This thing. And we just showed this has a GCF of 1. That's no accident. Whatever is left over has to have a GCF of 1. And just some other things that hopefully you picked up. If a polynomial, right, has a non-zero constant, a constant term, that means m has to be 0. In other words, the GCF here can only be a number. I mean, that's actually what happened here, right? We had a non-zero constant term, a term with no variables, okay? A term with no variables. And also, just like over here in the previous example, if a coefficient is 1, that forces b to be 1. Because the only factor of 1 is 1. In fact, if a polynomial has a non-zero constant term, 1, so if 1 is a non-zero constant term, wait, let me say it again. If 1 is a constant term for a polynomial, that forces the GCF to be 1. And we'll actually see that here. Namely, let's find the GCF of this thing. Okay, well, the smallest exponent of x here, right? That's 0, right? Because we have a non-zero constant term. Again, we could use the convention here, x to the 0 is 1. We could do that. Although it's not really precise. But again, since there's a non-zero constant term, that tells us m has to be 0. Okay, what about b? What about the coefficients and the non-zero constant term? Well, we have 4, we have 8, we have 1. What are the factors of each of these? The factors of 4 are 1, 2, and 4. The factors of 8 are 1, 2, 4, and 8. 1, 2, 4, and 8. The factors of 1, right, is just 1. So the only factor of 1 is 1. The only common factor is 1. That forces b to be 1. So altogether, we get b is 1, m is 0. That is, the GCF is 1. So this example is just really illustrating the bottom statement here. That if you have a polynomial which has 1 as the non-zero constant term, the GCF has to be 1. Okay, that's good. All right, are there any questions on this? Okay. Well, so that's one method of factoring, right? You know, that's one method, finding the GCF and factoring it out. But it's really good to have more than one method. So let's look at another one. This method has to do with trinomials, polynomials that is, that have 3 terms, okay, like so. And now to factor this, I mean, the book goes into it. I did write some stuff here. It boils down to finding 2 numbers, B and D, whose product is the constant term and whose sum is the coefficient of x. That's really what it boils down to. Okay, I mean, they do illustrate that with calculations in the book. I mean, it's not really terribly hard to see why this is true. But again, it boils down to looking for 2 numbers, B and D, that fill in these blanks. So the product has to be the constant term, C. The sum is the coefficient of x. Like so. Good. So here's an example. Let's say we want to factor this thing. Let's say we want to factor. Okay, so we want 2 numbers whose product is 10 and the sum is 7. Okay, well, it is 10. So in other words, again, we want 2 numbers that fill in the blanks here, whose product is 10, whose sum is 7. Well, what about 10 and 1? Well, 10 times 1, that's 10. That's true. But 10 plus 1 is not equal to 7, right? That doesn't work. 10 and 1 are not going to work. What about this? 5 and 2. 5 times 2, that's 10. 5 plus 2 is 7. So these numbers are going to work. 5 and 2 are going to work. Okay. All right, so that tells us this trinomial, this polynomial, excuse me, must equal x plus 5 times x plus 2. And you could check it by just multiplying. It turns out if you multiply, yeah, it does work. So that's really the technique for factoring these kinds of polynomials. So, you know, again, you want 2 numbers whose product is the constant term, well, 2 integers, I should say, whose product is the constant term, and sum is the coefficient of x. Okay. All right, so I guess we'll stop here. So if I don't hear from you, I do have office hours today, but if I don't hear from you, you know, have a great weekend. Okay, so we'll